Welcome back. In the previous chapter, we had made the world more realistic by allowing for horizon-dependent interest rates. In this video, we crank up the realism hugely, except for treasuries, where we were already perfectly realistic. Things get a lot more interesting if we're going to add uncertainty. However, this means I first need to make sure that your statistics background is brought back up to speed. Let's get started. We now need to describe an uncertain future. For this, we need statistics. The brisk overview in what we're doing here is just the minimum needed. Some crazy people, like myself, actually enjoy statistics, perhaps because this chapter is illegal in some states. Attend the rest of this course at your own risk. For example, here is something from the New York Penal Code. Persons pretending to forecast the future shall be considered disorderly under Subdivision 3, Section 901 of the Criminal Code and be liable to a fine of $250 and/or 6 months in prison. So please don't watch this video while you are in New York State. Let's get criminal then. A random variable, often written with an intimidating tilde over the variable, like x tilde, is not an ordinary algebra variable that holds some kind of value like the number 3. It's best thought of as a histogram with a name. So x is really a histogram. It's a cloud of possible outcomes from some sort of randomizing device. That could be a coin or a card draw, or a normal draw from a normal distribution, but all of this is defined by its histogram. So, for example, here is a random variable. I'm going to call this random variable D for die, and there is 6 possible outcomes from throwing a fair die, which is, in this case, equivalent to losing $6, earning $36, losing $12, or earning $150. Well, $150 is much more likely. There are 3 outcomes that are just like this. Just to make sure, do you remember what a histogram is? Draw it.
Please pause this video now, answer the question on a piece of paper, and then continue.
This is how the histogram looks like. The probability is on the y-axis. The value is on the x-axis. So on the x-axis, you've got the dollar amounts that we just had, -6 plus 36. And on the y-axis, I got the probability. Now, because 150 appears 3 times, the bar is 3 times as high for the 150 as it is for the other possible outcomes. Histograms can visually look quite different depending on the breaks. So I'm going to show you 2 histograms that are for exactly the same set of draws. Here's the first. As you can see, it looks like I have a bimodal distribution. I have 2 peaks here. This is a histogram of exactly the same outcomes. And now it no longer looks bimodal. It looks more like a normal distribution. So, very easy to be misled. Don't trust histograms too much. I want you to think of the rates of returns of investment assets of being histograms. And what we need to do is we need to measure risk and reward of these histograms. So, first, we want to measure reward. By far the most common measure of reward is the expected rate of return. By far the most common measure of risk is the standard deviation of the expected rate of return. They're sometimes called risk and reward. Those are odd names, but they're very common. It would be better to call them risk and expected reward. So let's do the reward. What is it that we have to expect? E, and then in parentheses, or sometimes even omitted, E of something is the standard notation for the expected value of something. For example, E of d tilde is the expected value of the random variable d. To reduce clutter, I may drop the tilde and just call it E of d. And sometimes people will just write E space d. You can calculate this expected value from the histogram, and it's easy to do. You multiply each outcome by the probability of this outcome, and then you sum up the terms. And if all outcomes are equally likely, you can just calculate the average. So, think of the true population value as the mean of the random variable if you draw infinitely many samples. So if I take this die that I just had before and I throw it 1,000,000 times, then I'm going to be very close to the true population values. The average, the mean, and the expected value are often used interchangeably, even if it's only almost correct, because the expected, we don't know yet what the outcome is going to be. Well, we do know what the expected value is, we can calculate that, but we're going to do this on something for which we don't know yet the outcome. The average, or the mean, is something that refers to a specific sample that we have already drawn. The average of the data is going to be the realization of the expected. So on average, we expect the average to be the expected. So calculate this for me. What is the expected payoff of D?
Please pause this video now, answer the question on a piece of paper, and then continue.
Easy. 1/6 times minus $6 plus 1/6 times plus $36 plus 1/6 times minus $12 plus, because we have 3 of them, 3/6 times $150. Add that up, weight it, and you get $78. Is E of D a random value or a number?
Please pause this video now, answer the question on a piece of paper, and then continue.
It's not a random variable, but a number. It's something that I can calculate today. I already know it. D is the outcome. That's the random variable. E of D is something I know today. Is the expected payoff always the most likely outcome?
Please pause this video now, answer the question on a piece of paper, and then continue.
No. In fact, it can be an impossible outcome. What is the average number of children per woman? It isn't 1, 2, or 3. It's 2.2, and we don't cut up kids. So if the most common outcome is what you're interested in, what you want is called the mode. Are half of all outcomes below the mean?
Please pause this video now, answer the question on a piece of paper, and then continue.
Again, no. This is only the case for symmetric distribution. If this is the number that you're interested in, you want the median. If you repeat a bet an infinite number of times, you should expect to receive the expected return, not the median or the mode. And it is this expected rate of return that is the main measure of reward in finance. Now, mode, median, and mean are all called central statistics. Sometimes they're called first moments. That comes from something from mechanics. We don't usually care about this. We also don't care about the mode or the median. We really care only about the mean, and that's going to be what we will be using in this class. Another important question in finance is to measure news, things that are unexpected. And the way you measure the unexpected is you take whatever the outcome is, the realized, and you subtract off the expected. So for example, Bayern München is expected to lose to Real Madrid with 80% probability. Sadly, Real Madrid is the better team. The expected outcome, if I call 1 to be a win and 0 to be a loss, is 20%. So if Bayern Munich loses, the news is minus 20%. If they win, the news is plus 80%. Who likes the Spanish anyway? Even their schnitzels aren't as good. Though, in fairness, our paellas aren't as good either. But their soccer teams, oh well, they're much better than ours. Now we're going to move on to risk. Expect the unexpected. What we want to do is quantify how much unexpected we expect. These are sometimes called second moments, again from mechanics. The variance is defined as the expected value of d minus e of d squared. So the variance, roughly speaking, is the expected squared deviation from the mean. Since we know the deviation from the mean is news, it's the expected squared news. It's just pseudo-intuitive, close enough. Now, if you have infinitely many draws, what it would mean is, what you want to measure is the mean of d minus the mean of d squared. Then you have the population variance. The units and meaning of a variance is usually completely incomprehensible, except for one thing. Higher means more volatile. So, for each outcome, for our die, please calculate the news first.
Please pause this video now, answer the question on a piece of paper, and then continue.
So all we need to do is we subtract off the expectation, which is $78, from each outcome. So take a look at my table here, probability 16, 16, 16, 36. Then I have the outcomes. Then I have the outcome minus the expected outcome. So for the first outcome, this is minus $84. If you take all of those outcomes and you take the probability weighted mean, that is 16161636, that is always 0. On average, news, the unexpected, must be 0. Otherwise, it's not news. Next step, for each outcome, square the news.
Please pause this video now, answer the question on a piece of paper, and then continue.
Okay, take the demeaned numbers, which we just calculated, square them, write them into the same table. 7,056, 1,764, 8,100, 5,184. There is a strange unit on them. That's $. That's because what you have done here is you've taken a dollar figure and you've squared it. So you need $. What does it mean? Nobody knows. What's the variance?
Please pause this video now, answer the question on a piece of paper, and then continue.
All we need to do is take the probability weighted mean of those squared numbers. So you do that, out comes the number 5,412. So the variance is 5,412, $. The more interesting measure in most practical use is the standard deviation. That is the square root of the variance. Take the variance from the previous example. Square root, $73.57. That is a very meaningful unit. So if you look at our previous die throw, it also gives us a nice rough measure of where this is. I think of the standard deviation as the typical deviation from the mean of the next row. It's not entirely correct because outliers and other things are weighted a little bit different, but it's close enough. If the variance is higher, the standard deviation is higher and vice versa. So more risk is always more variance and more standard deviation. But only standard deviation has units that are meaningful. In many cases, it's vanilla versus chocolate. Of course, chocolate is always better, which is why you prefer the standard deviation. This is the standard deviation, which we just calculated to be $73.57. So I've put the mean in. You can see the mean as the vertical line, and then the standard deviation. So it gives you a good idea of what it is that we have as a risk measure here, of how far away from the mean you're likely to be. We calculated the population variance. This is correct because we did not have to estimate the probabilities. The physical process of the die gave us the correct probabilities exactly. If we have to calculate the sample variance, we don't divide by n, the number of observations, but by n minus 1. Remember, when we sample, we usually assume that each draw is equally likely, but then in the end, we don't divide by the number of draws, but one less. So we use the sample variance when we only have data samples, and we even had to estimate the mean. Here's an example. You've just drawn 1, 2, and 3. For the sample variance, you don't take 2, which is 1 squared plus 1 squared, and divide by 3. You have to divide by 2. So the sample variance is 1, and the population variance is 2/3. Let's do a historical data example, because this is really what we're going to use this for. We're not going to play around much with dice. Assume the expected rate of return and the standard deviation of return have to be estimated from only 4 historical stock returns: plus 10%, minus 5%, plus 20%, and plus 15%. Calculate for me, please, the expected rate of return and the standard deviation.
Please pause this video now, answer the question on a piece of paper, and then continue.
Here's the answer. In the first row, I've got the 4 rates of returns. It's easy to add them up. Plus 10, minus 5, plus 20, 15. That comes out to 40. And I've got 4 observations, so my mean is 10%. In the second row, I subtract off the mean. So for the first observation, that is 0. For the next one, it's minus 15%. Then it's plus 10% and plus 5%. The next row, I square this. So it's 0%, then it's 225%. You could think of that as dividing by 100 and dividing by 100 again. It's 100% and 25%. The sum squares, if you add them all up, is 350%. 225 plus 100 plus 25. If these were true population probabilities of 1/4 each, that is, I would know that the true mean is 10%, then I would divide this sum by 4, and I would get 87.5%. This would give me a standard deviation of about 9.35%. But these are just historical samples, and I have to estimate the population mean from them too. So what I need to do for the standard deviation and the variance, I have to divide the sum by n minus 1, 3, which gives us 116.67%. This translates into a standard deviation of 10.8%. One of the reasons why I had to tell you this is because Excel always tells you the sample standard deviation. And if you don't know this, sooner or later, this is going to bite you. If you really want to get the population standard deviation from Excel, you have to use standdef-p instead of standdef. Similarly, var-p instead of var. If you have a large data set with hundreds of observations, it doesn't matter whether you divide by n or n minus 1. But in small samples, it does matter, and I didn't want you to get baffled why Excel would give you a different number than the ones we use in our slides. That's it for this video and for basic statistics. In the next video, we'll be looking at how to work statistics, not just with individual investments, but with entire investment portfolios. See you soon. Bis bald.
Can I tell you what our previous business school dean said at one of our faculty meetings?
What?
I want every faculty member to be an above average teacher.
Really?
Really?
This was mean?